time. The thing that, when we are young, we believe we have plenty of, and as we get older, we believe is slipping away. When you're a kid, summers feel endless. Weekends stretch on forever, and the years seem to crawl by. But then something shifts. Days start blurring together. Weeks vanish. Suddenly, you're looking back and wondering where all the time went. You check your phone a dozen times a day, schedule every hour, count down to deadlines and birthdays, desperately trying to hold on to something that keeps speeding up. But what if I told you time is just an illusion? If this kind of mind-bending exploration grabs you, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in, because by the end of this journey, you might never look at a clock the same way again. Imagine waking up tomorrow morning and checking your phone. The clock says it's 8 a.m., just like always. You get ready for work, go through your routine, and then suddenly you notice something strange. Your clock is running backward. 9 a.m. becomes 8:59, then 8:58. Or imagine realizing that today is repeating yesterday. The same conversations, the same events, happening all over again. This sounds like science fiction, right? Like a movie plot. But the deeper you look into physics, into the actual laws that govern our universe, the stranger time becomes. And by the end of tonight, you're going to see why some of the smartest physicists in history have spent their entire careers trying to understand what time actually is. Time seems obvious. It flows forward. You were born, you grew up, you're living now, and someday you'll die. Past, present, future. One direction, always moving forward. You can remember yesterday, but you can't visit it. You can plan for tomorrow, but you can't see it yet. This seems so fundamental, so basic, that questioning it feels absurd. But that's exactly what we're going to do tonight. We're going to question everything you think you know about time. And fair warning, this is going to mess with your head in ways you won't expect. Let's start with the most basic question. What is time? You might say it's what clocks measure, but that just moves the question. What are clocks measuring? You might say time is the thing that separates events, that keeps everything from happening at once. But why does it only go forward? Why can't you go backward? You might say time is change itself, the process of things happening. But then, what about things that don't change? Do they exist outside of time? These aren't just philosophical puzzles. They're real questions that physicists have been wrestling with for over a century. And the answers they've found are stranger than almost anyone expected. Time is not what it seems. It's not universal, not constant, not even necessarily real in the way you think it is. And understanding this changes everything about how you see the universe and your place in it. Let me give you a preview of where we're going tonight. We'll start with everyday time, the time you experience in your daily life. Then we'll look at how classical physics treated time as absolute and universal. After that, we'll dive into Einstein's relativity, which showed that time is flexible, stretching, and compressing depending on speed and gravity. Then we'll enter the bizarre world of quantum mechanics, where time becomes even stranger. We'll explore why time only goes forward, the arrow of time driven by entropy. We'll talk about time travel, both the theoretical possibilities and the fundamental barriers. And finally, we'll step back and ask the big question, is time real at all? Or is it just a useful illusion our brains create? This is going to be a journey, a long one, but by the end you're going to see your watch, your calendar, your entire life differently. You're going to understand why time is one of the deepest mysteries in physics, and why solving that mystery might be the key to understanding the universe itself. So let's begin with what we know best, the time we experience every day. You wake up in the morning, you check your phone and it says 7 a.m. You have to be at work by 9 a.m., so you have 2 hours. You shower, eat breakfast, get dressed, commute. Each activity takes time. Some activities feel like they take forever. Waiting at a red light feels like an eternity. Other activities fly by. Watching a great movie, and suddenly 2 hours have passed in what felt like 20 minutes. But underneath all of this, you have a clear sense that time is flowing, moving forward, carrying you from morning to afternoon to evening to night. This experience of time is so fundamental to being human that it's hard to imagine life without it. Your entire identity is built on time. You remember your past. You remember being a child, going to school, the experiences that shaped you. Those memories feel real and solid. They happened in the past. You experience the present, right now, this moment, reading these words or listening to this video. This is now. This is happening. And you anticipate the future. Tomorrow, next week, next year. You make plans. You set goals. You worry about what might happen or hope for what could happen. This sense of time flowing from past through present to future is called the psychological arrow of time. It's how humans experience time. It's built into our consciousness, into our language, into how we think. We say things like, time flies, or time drags, or I'm running out of time. We treat time like a thing, like a river that's flowing past us, carrying us along whether we want to go or not. But here's the first strange thing about time. Different people experience it differently. Think about the last time you were waiting for something important. Maybe waiting for test results from a doctor. Maybe waiting to hear back about a job application. Maybe waiting for someone you care about to text you back. Those minutes felt like hours, didn't they? The clock seemed to slow down. You kept checking it, and barely any time had passed. 5 minutes felt like 20. You'd swear the clock was broken, that time itself had slowed to a crawl. Now, think about the last time you were doing something you loved. Playing a game, talking with friends, working on a project you're passionate about. Hours passed like minutes. You looked up, and suddenly it was late, and you had no idea where the time went. You started at 2 in the afternoon, and suddenly it's 8 at night, and you haven't eaten dinner. This isn't just a saying. It's a real psychological phenomenon. Your brain's perception of time changes depending on what you're doing and how you're feeling. When you're bored or anxious, your brain is hyper-aware of time passing. It's constantly checking, constantly monitoring, so it feels like more time is passing. It's like watching water boil. When you stare at the pot, waiting for bubbles to form, it feels like it takes forever. But if you walk away and do something else, suddenly the water is boiling and you didn't even notice. Your attention to time makes time feel slower. When you're engaged and focused, your brain stops monitoring time. It's too busy with the task at hand. All your mental resources are devoted to what you're doing, whether that's solving a puzzle, having a deep conversation, or creating something. Time becomes irrelevant. Your brain isn't tracking it anymore. So when you finally check the clock, you're shocked by how much time has actually elapsed. This state is what psychologist Mihaly Csikszentmihalyi calls flow, a state of complete absorption where you lose track of time entirely. Scientists have studied this extensively. In one experiment, researchers had people estimate how long various activities took. People consistently overestimated the duration of boring tasks and underestimated the duration of engaging tasks. A 5-minute wait in line felt like 10 minutes. A 30-minute engaging conversation felt like 15 minutes. The actual time that passed was measured precisely by clocks, but the subjective experience of that time varied wildly depending on what people were doing and feeling. There's even stranger examples. In life-threatening situations, many people report that time seemed to slow down. A car accident that took 2 seconds feels like it lasted 10 seconds in memory. You hear about this all the time. Someone's in a crash and they say, everything went into slow motion. They describe seeing the other car approaching, having time to think multiple thoughts, seeing details with incredible clarity, and feeling like the whole event took much longer than it actually did. War veterans describe bullets moving slowly through the air. Athletes describe crucial moments of competition unfolding in slow motion. Is time actually slowing down in these moments? Now, time doesn't actually slow down during these events. Your brain doesn't suddenly start processing information faster. If that were true, you'd be able to perceive things that normally happen too fast to see. Scientists tested this by having people in freefall try to read numbers flashing faster than people can normally perceive. Even though the people in freefall felt like time had slowed down, they couldn't read the numbers. They weren't processing information any faster. Instead, what happens is your brain records more memories during high-stress events. When your brain detects danger, it goes into a heightened state. Adrenaline floods your system. Your amygdala, the part of your brain that processes emotions and fear, becomes extremely active. And crucially, it starts laying down much more detailed memories than normal. It's recording not just the main events, but every little detail. The sound of screeching tires, the smell of burning rubber, the exact angle of the approaching car, the color of the sky, the feeling of your hands on the steering wheel. All of these details get encoded into memory. Later, when you remember the event, you have all these extra memories, this incredibly rich, detailed recording of what happened. And your brain makes an assumption. It assumes that if you have more memories of an event, the event must have lasted longer. After all, normally, longer events produce more memories than shorter events. A 2-hour movie produces more memories than a 2-minute video. So, when you have an unusually large number of memories from a 2-second event, your brain incorrectly concludes that the event must have lasted longer than 2 seconds. The event feels like it was in slow motion, even though it happened in real time. Time didn't slow down. Memory formations sped up. This tells us something important. Even in everyday life, even before we get to physics and relativity and quantum mechanics, time is already constructed by your perception. It's not a fixed, external thing. It's something your brain creates based on what's happening around you and inside you. 2 people can experience the same objective duration, say 60 seconds, and have completely different subjective experiences of how long it felt. A child waiting for Christmas morning experiences time crawling by. An adult having fun at a party experiences time flying by. Same universe, same laws of physics, completely different experiences of duration. But we're not just stuck with our subjective experience. Humans figured out long ago how to measure time objectively, how to create tools that track time independent of our perception. The history of timekeeping is actually fascinating because it shows how desperately we needed to measure time accurately and how hard it was to do. Ancient civilizations measured time using the natural cycles they observed. The sun rose and set. That's a day. The moon went through its phases. That's a month. The seasons changed. That's a year. These are all based on astronomical movements, on the rotation of Earth and its orbit around the Sun and the Moon's orbit around Earth. Early humans used these cycles to organize their lives. They knew when to plant crops based on the seasons. They knew when to expect floods or droughts. They knew when animals would migrate. Time was tied to nature, to the rhythms of the world around them. This was time you could see and feel. The sun was your clock. The moon was your calendar. But these natural cycles had limitations. A day is a long unit. What if you need to measure smaller durations? What if you need to coordinate activities that happen within a single day? You need to divide the day into smaller parts. The Babylonians divided the day into 12 parts, which became our hours. They chose 12 because it's divisible by many numbers, 2, 3, 4, 6. This made calculations easier. Each hour was divided into 60 minutes, and each minute into 60 seconds. Again, 60 because it has many divisors. This sexagesimal system, base 60, comes down to us from Babylonian mathematics over 4,000 years ago. Every time you check the time and see hours, minutes, and seconds, you're using a system invented in ancient Mesopotamia. The first clocks were incredibly simple. Sundials measured the shadow cast by the sun. As the sun moved across the sky, the shadow moved, marking the passage of time. You'd place a vertical stick in the ground, and the shadow it cast would move in a predictable arc throughout the day. By marking the positions of the shadow, you could divide the day into hours. Sundials are elegant and require no power or maintenance. But sundials only work when the sun is shining. They're useless at night or on cloudy days. They also don't work well at high latitudes where the sun's angle changes dramatically with the seasons. And they're completely useless indoors. Water clocks were developed to solve this problem. The idea is simple. Water flows from one container to another at a steady rate. By measuring how much water has moved, you can measure how much time has passed. The Egyptians used water clocks as early as 1600 BC. Some water clocks were very sophisticated, with mechanisms to keep the flow rate constant even as the water level changed. But water clocks weren't very accurate. The flow rate depends on temperature, on the size of the hole the water flows through, on whether the hole gets clogged with sediment. And they needed constant refilling. Still, for thousands of years, water clocks and sundials were the best options available. Candle clocks were another early timekeeping method. You'd mark a candle with lines at regular intervals. As the candle burned, you could see how much time had passed by, which mark the candle had burned down to. The Chinese and Japanese used candle clocks extensively. Some were quite elaborate, with metal balls embedded in the wax at specific heights. As the candle burned down to each ball, the ball would fall and make a sound, marking the passage of an hour. These were the alarm clocks of the medieval period. The development of mechanical clocks in medieval Europe was revolutionary. These clocks used gears and weights to measure time with much greater precision. The key innovation was the escapement mechanism, a device that converts continuous rotation into discrete ticks. A weight pulls on a gear, making it want to spin. But the escapement only lets it advance one tooth at a time, tick by tick. This creates a regular rhythm that can be counted. For the first time, you could divide the day into hours and minutes and track them reliably, day and night, rain or shine, indoors or outdoors. This changed society in profound ways. Suddenly you could coordinate activities. You could say, "Meet me at 3 o'clock," and both people would know exactly when that was, even if they were indoors and couldn't see the sun. Work could be scheduled. Factories could operate on shifts. Church bells could ring at precise times. Time became something you could manage and control. The Industrial Revolution wouldn't have been possible without accurate clocks. When workers arrive at random times and leave at random times, you can't run a factory. You need coordination. You need schedules. You need time. But even the best mechanical clocks weren't perfect. They'd gain or lose minutes over the course of weeks or months. Temperature changes affected the metal components. The oil in the gears would thicken or thin. For most purposes, this was fine. Being a few minutes off doesn't matter much for daily life. But for navigation, it was a serious problem. Sailors needed accurate clocks to determine their longitude at sea. Here's how that works. Latitude, your north-south position, is easy to determine. You measure the angle of the sun, or North Star, above the horizon. But longitude, your east-west position, is harder. The trick is to compare local time to the time at a reference point, usually Greenwich, England. If local noon happens 3 hours after noon in Greenwich, you know you're 3 time zones west of Greenwich, about 45 degrees of longitude. But to do this calculation, you need to know what time it is in Greenwich, which means you need a clock that keeps accurate time even on a rocking ship in the middle of the ocean for months at sea. This was such an important problem that the British government offered a huge prize for anyone who could solve it. The Longitude Prize, established in 1714, offered £20,000, equivalent to millions today, for a method to determine longitude at sea within 30 nautical miles. John Harrison, a self-taught clockmaker, spent decades developing marine chronometers, incredibly precise mechanical clocks designed to keep accurate time even on a rocking ship. His 4th chronometer, completed in 1759, was accurate to within 1 second per day, even after months at sea. This was revolutionary. The invention of reliable chronometers in the 18th century made long-distance sea navigation much safer and more accurate. It opened up global trade and exploration in ways that wouldn't have been possible otherwise. Today, we have atomic clocks. These are the most precise timekeeping devices ever created. They measure time based on the vibrations of atoms, specifically cesium atoms. A cesium atom vibrates at an incredibly precise frequency, exactly 9,192,631,770 times per second. That's the definition of a second. An atomic clock counts these vibrations. Because atoms behave the same way everywhere in the universe, governed by the same physical laws, atomic clocks are extraordinarily accurate. The best atomic clocks in the world would only lose or gain about 1 second in 30 million years. This precision is essential for modern technology. GPS satellites, for example, rely on atomic clocks. Each satellite has an atomic clock on board, and these clocks need to be synchronized to within billionths of a second for the GPS system to work accurately. Your phone can pinpoint your location to within a few meters or feet because satellites in orbit are keeping time to incredible precision. Time has gone from something we measured with shadows and water to something we measure with the vibrations of atoms. We've gotten really good at measuring it, but just because we can measure time precisely doesn't mean we understand its nature. We've built better and better clocks, but that doesn't tell us what the clocks are actually measuring. Is time a real thing that flows like a river? Is it a dimension, like space? Is it just a convenient way to organize events? These are the questions physics tries to answer, and the answers turned out to be far more surprising than anyone expected. Before we get to modern physics, we need to understand how classical physics, the physics of Isaac Newton, treated time. Because, for about 200 years, from the late 1600s to the early 1900s, scientists thought they had time figured out. They were wrong. But understanding what they thought and why they thought, it is important for understanding what came next. Isaac Newton published his laws of motion and universal gravitation in 1687 in a book called Philosophia Naturalis Principia Mathematica, or The Mathematical Principles of Natural Philosophy. This work formed the foundation of classical physics, a system for understanding how objects move and interact. And central to this system was Newton's concept of time. Newton believed that time was absolute, that it flowed at the same rate everywhere in the universe. A second on Earth was the same as a second on the Moon, the same as a second in a distant galaxy. Time was universal, constant, unchanging. It was like a cosmic clock ticking away the same for everyone and everything. In Newton's own words from the Principia, absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. This is a bold statement. Newton is saying that time exists independently of anything happening in the universe. Even if all matter and energy disappeared, even if the universe was completely empty, time would still flow forward at its steady pace. Time is the background, the stage on which events occur. But the stage exists whether or not there are any actors on it. In Newton's view, time was completely separate from space. Space was where things happened. Time was when things happened. They were independent. You could describe an event by saying where it occurred and when it occurred, but the where and when were completely different types of information. Space had 3 dimensions: length, width, and height. You need 3 numbers to specify a location in space. Time was one-dimensional, just moving forward. You only need 1 number to specify a moment in time. And time had no connection to space. They existed separately, each doing their own thing. Moving through space didn't affect your movement through time. Being in one location versus another didn't change how fast time flowed for you. This made perfect sense for everyday experience. If you drop a ball, it falls at the same rate whether you drop it in New York or London or Tokyo. The time it takes doesn't depend on where you are. If 2 events happen at the same time on Earth, say 2 people clapping their hands at exactly noon, Newton would say those events happened simultaneously. They happened at the same time, and that simultaneity was absolute. Everyone in the universe would agree that those 2 claps happened at the same moment, even if they didn't see or hear them until later, because light and sound take time to travel. The events themselves happened simultaneously in absolute time, regardless of when any particular observer became aware of them. Newton's laws of motion described how objects move through space over time. The first law says an object at rest stays at rest, and an object in motion stays in motion unless acted on by a force. The second law says force equals mass times acceleration. If you push on something, it accelerates in proportion to how hard you push and in inverse proportion to how massive it is. The third law says every action has an equal and opposite reaction. If you push on a wall, the wall pushes back on you with equal force. These laws are deterministic. If you know an object's position and velocity at one moment, and you know all the forces acting on it, you can calculate exactly where it will be at any future moment. You can also calculate where it was at any past moment. The mathematics works both forward and backward in time. The universe, in Newton's view, was deterministic. It was like a giant clockwork mechanism. God wound up the clock at the beginning, set the initial conditions, and it's been ticking along ever since, following precise mathematical laws. Every effect has a cause. Every cause leads to an effect, all marching forward through absolute time. This clockwork universe had profound implications. Pierre-Simon Laplace, a French mathematician and astronomer working in the late 1700s and early 1800s, took Newton's ideas to their logical conclusion. He proposed what's now called Laplace's demon. Imagine a being, a demon, that knows the position and momentum of every particle in the universe at one moment in time. This demon also knows all the laws of physics. With this information, Laplace argued, the demon could calculate the entire past and future of the universe with perfect accuracy. The future was already determined by the present. Nothing was random. Nothing was uncertain. Everything unfolded according to mathematical law. Time was just the parameter that tracked this unfolding. This has uncomfortable implications for free will. If the future is completely determined by the present, if your actions are just the inevitable consequences of the positions and momenta of all the atoms in your brain, which are themselves determined by their past positions and momenta going all the way back to the Big Bang, then in what sense do you have free will? Are you really making choices? Or are you just following a predetermined script written into the initial conditions of the universe? Newton himself was religious and believed in free will and divine intervention. He didn't think the universe was purely mechanical. He thought God could intervene and adjust things when necessary. But the mathematics of his laws suggested otherwise. Once you set the initial conditions and let the laws operate, everything else follows inevitably. The universe computes its own future by simply existing. Each moment determines the next moment through the laws of physics. For 2 centuries, this view of time worked incredibly well. Newton's laws accurately predicted the motion of planets, the trajectory of cannonballs, the behavior of pendulums, the orbits of comets. They were used to build machines, design bridges, navigate ships, predict eclipses. The Industrial Revolution was built on Newtonian mechanics. Steam engines, factories, railroads, all of these relied on understanding how forces cause motion over time. Classical physics was enormously successful. And because it was so successful, people assumed its foundations were correct. Time was absolute. Space was absolute. They were the fixed stage on which the universe performed. Philosophers debated the nature of time. Immanuel Kant, writing in the 1700s, argued that time and space were not external realities, but rather forms of human intuition. They were the way our minds organized sensory experience. We can't perceive anything except as existing in space and time, because space and time are built into how we perceive. But Kant still thought that within our perception, time was absolute and universal. All observers shared the same time. Scientists used Newtonian mechanics to discover new planets. In the mid-1800s, astronomers noticed that Uranus wasn't following its predicted orbit. Something was pulling on it gravitationally. Using Newton's laws, they calculated where an unknown planet would need to be to explain Uranus's motion. They pointed their telescopes at that location and found Neptune. This was a stunning confirmation of Newtonian physics. You could predict the existence and location of an entire planet just by doing the mathematics. But there were some puzzles, some things that didn't quite fit. One of the biggest was light. By the mid-1800s, physicists had figured out that light was a wave, an electromagnetic wave. James Clerk Maxwell, a Scottish physicist, had unified electricity and magnetism into a single theory in the 1860s. His equations showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. These fields could oscillate together, creating a wave that propagates through space. And when Maxwell calculated the speed of these electromagnetic waves, he found they traveled at exactly the speed of light. This was too much of a coincidence. Light must be an electromagnetic wave. But here was the problem. Waves need something to wave in. Water waves move through water. Sound waves move through air. If you remove the air, sound can't travel. That's why there's no sound in space. So what did light waves move through? Light obviously travels through empty space. Sunlight reaches Earth through the vacuum of space. So there must be something there, something filling all of space that light waves move through. Scientists propose something called the luminiferous ether, or just the ether for short. This was supposed to be an invisible substance that filled all of space. It had to have very strange properties. It had to be extremely rigid to allow light waves to travel so fast, yet offer no resistance to solid objects moving through it. Planets move through space without slowing down, so the ether couldn't produce drag. Yet, it had to be substantial enough to carry light waves. This seemed contradictory, but physicists assumed the ether must exist because waves need a medium. If the ether existed, then there should be an absolute reference frame, a way to measure absolute motion through space. Newton's laws say there's no such thing as absolute motion, only relative motion. If you're on a train moving at constant speed, you can't do an experiment inside the train to tell that you're moving. Physics works the same whether you're moving or stationary, but the ether would change that. If the ether fills all of space and is stationary, then you could measure your motion relative to the ether. Earth moves through space as it orbits the sun. Earth orbits at about 30 kilometers per second, or about 18 miles per second. That's fast. So Earth should be moving through the ether, like a boat moving through water. And just like a boat experiences a headwind when it moves into the wind and a tailwind when it moves with the wind, light should travel at different speeds depending on whether Earth is moving toward the light source or away from it. If Earth is moving through the ether in one direction, light coming from that direction should move slower relative to Earth because we're moving into it. Light coming from the opposite direction should move faster because we're moving away from it. In 1887, two American scientists, Albert Michelson and Edward Morley, designed an incredibly clever experiment to detect this motion through the ether. They built what's called an interferometer. Here's how it worked. They took a beam of light and split it into two perpendicular beams using a half-silvered mirror. One beam went north-south, the other went east-west. Each beam hit a mirror and bounced back. Then the beams were recombined. If one beam took longer to make its round trip than the other, the beams would be slightly out of phase when they recombined, creating an interference pattern of light and dark bands. If Earth was moving through the ether, say in the east-west direction, then the beam going east-west would be going with and against the ether wind, like swimming downstream and then back upstream. The beam going north-south would be going across the ether wind, like swimming across a river current. Even though both beams travel the same distance, the times would be different because of the ether wind. The difference would be tiny, but Michelson and Morley's apparatus was sensitive enough to detect it. They set up their experiment in Cleveland, Ohio, in a basement to minimize vibrations. They floated the entire apparatus on a pool of mercury so it could be rotated smoothly. They ran the experiment at different times of day. They ran it at different times of year when Earth was moving in different directions in its orbit. They expected to see a clear signal, a shift in the interference pattern that would tell them how fast Earth was moving through the ether. They found nothing, no difference. Light traveled at exactly the same speed in every direction, regardless of Earth's motion. The interference pattern didn't shift. It was as if the ether wind didn't exist. They repeated the experiment with greater and greater precision. Still, nothing. Other scientists repeated the experiment in different locations. Same result. Light always traveled at the same speed, regardless of the direction of measurement or the motion of Earth. This result was deeply, deeply puzzling. If light is a wave in the ether, and Earth is moving through the ether at 30 kilometers per second or 18 miles per second, why doesn't the speed of light change? Scientists proposed various explanations. Maybe Earth somehow drags the ether along with it, so we're always stationary relative to the local ether. But that didn't make sense. How could Earth drag an invisible substance that offers no resistance to motion? Maybe the ether isn't quite what we thought. Maybe it has properties we don't understand. Maybe the experiment had some flaw, some systematic error they hadn't accounted for. But none of these explanations really worked. The simplest explanation, that there is no ether and that light simply doesn't need a medium to propagate through, seemed crazy. How could a wave exist without something to wave in? Yet that seemed to be what the experiment was suggesting. The null result of the Michelson-Morley experiment was a crack in the foundation of classical physics. A hint that something fundamental was wrong with how we understood space, time, and motion. For almost 20 years, physicists puzzled over this result. Various proposals were made. Some tried to modify Maxwell's equations. Some tried to modify Newton's laws. Some proposed that objects physically contract in the direction of motion through the ether, which would explain why the experiment detected nothing. This contraction idea, proposed by George Fitzgerald and Hendrik Lorentz, actually came close to the truth. But they thought contraction was a physical effect, caused by motion through the ether, not a fundamental feature of space and time themselves. The answer came from a young patent clerk in Switzerland. His name was Albert Einstein, and in 1905, at the age of 26, he published a paper that would revolutionize physics and completely overturn Newton's absolute time. The paper was titled "On the Electrodynamics of Moving Bodies." Today, we call it special relativity, and it changed everything. Einstein started with two simple postulates. First, the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a perspective that's moving at constant velocity, not accelerating. If you're sitting still in your room, that's an inertial frame. If you're on a train moving at constant speed in a straight line, that's also an inertial frame. Einstein said that physics works the same way in both. You can't do an experiment that tells you whether you're really moving or really at rest. All motion is relative. There's no absolute standard. Second, the speed of light in vacuum is constant for all observers, regardless of their motion. This directly addressed the Michelson-Morley result. Einstein simply accepted it as a fundamental fact. Light always travels at the same speed, about 300,000 kilometers per second or 186,000 miles per second, no matter how fast you're moving or which direction you're going. These two postulates seem simple, almost obvious, but they have radical consequences. If the speed of light is constant for everyone, and if physics works the same way in all inertial frames, then time cannot be absolute. Time must be relative. Different observers moving at different speeds will measure time differently. This is time dilation. Here's a thought experiment to illustrate this. Imagine you're on a train moving very fast, say half the speed of light. That's about 150,000 kilometers per second, or about 93,000 miles per second. You shine a flashlight straight up at the ceiling. From your perspective on the train, the light goes straight up and straight down. Simple. The beam goes from the flashlight to the ceiling and back. You measure the distance, say 2 meters, or about 6.5 feet. You measure the time it takes. Since light travels at 300,000 kilometers per second, or 186,000 miles per second, you calculate that the light took about 13 nanoseconds for the round trip. Nothing strange here. But now, imagine someone standing on the ground watching the train go by. From their perspective, things look very different. The light doesn't go straight up and down. The train is moving forward at half the speed of light. So the light follows a diagonal path. It goes up and forward as the train moves, then down and forward as it comes back. The light travels a longer distance from the ground observer's perspective than from your perspective on the train. Instead of traveling straight up 2 meters and straight down 2 meters for a total of 4 meters, or about 13 feet, it travels in a diagonal path that's longer, maybe 5 meters or about 16 feet total. The key insight is this: both observers must measure the same speed for light. That's the second postulate of special relativity. The speed of light is constant for all observers, regardless of their motion. Speed is distance divided by time. If the ground observer sees the light travel a longer distance, but the speed is the same, then the ground observer must measure more time passing. Time must run slower for you on the train compared to the person on the ground. From the ground observer's perspective, your clock is running slow, your heartbeat is slow, your thoughts are slow, everything about you is slow. This isn't an illusion or a trick of perception. It's not that your clock appears to run slow because of some delay in the light reaching the observer. Time actually passes at different rates for different observers depending on their relative motion. This is why we say time is relative. There's no universal time that everyone agrees on. Every observer has their own time, and these times don't match up if the observers are moving relative to each other. The mathematics of special relativity quantify this exactly. There's a formula called the Lorentz factor that tells you how much time dilates. The faster you move relative to another observer, the more extreme the time dilation becomes. At everyday speeds we're familiar with, like driving a car or flying in an airplane, the effect is tiny, unmeasurable without atomic clocks. If you drive across the country at 100 kilometers per hour or 60 miles per hour, you'll age a few nanoseconds less than someone who stayed home. That's billionths of a second. You'd never notice it, but at speeds approaching the speed of light, the effect becomes dramatic. At 90% of light speed, time dilation is about a factor of 2.3. Your clock runs about 2.3 times slower than a stationary clock. At 99% of light speed, it's a factor of 7. At 99.9%, it's a factor of 22. At 99.99%, it's a factor of 71. The closer you get to light speed, the more extreme the effect, asymptotically approaching infinity as you approach light speed itself. Imagine a spacecraft traveling at 99% of light speed. Due to time dilation, clocks on the spacecraft would run about 7 times slower than clocks on Earth from Earth's perspective. If the spacecraft traveled for 1 year, According to clocks on board, about 7 years would pass on Earth. The astronauts would return, having aged 1 year, while everyone on Earth aged 7 years. This is the famous twin paradox. One twin travels at high speed, the other stays home. When the traveling twin returns, they're younger than the twin who stayed behind. It sounds like a paradox, but it's not. It's a real consequence of time dilation, confirmed by countless experiments. Let's work through this carefully to understand why it's not actually a paradox. Imagine twin siblings, Alice and Bob. Alice stays on Earth. Bob gets into a spacecraft and travels to a star 4 light-years away at 99.9% of light speed, then turns around and comes back. From Earth's perspective, Bob's journey takes about 8 years. 4 years to get there, 4 years to get back, traveling at almost light speed. When Bob returns, Alice has aged 8 years. But for Bob, time has been running slower. At 99.9% of light speed, time dilation is a factor of about 22. So while 8 years passed on Earth, only about 4 months passed for Bob. Bob steps out of the spacecraft having aged only 4 months, while his twin sister Alice has aged 8 years. Bob is now significantly younger than Alice, even though they were the same age when he left. You might ask, isn't motion relative? From Bob's perspective, couldn't he say that he was stationary and Earth moved away and then came back? If that were true, wouldn't Alice be younger when they reunite? This is why it's called a paradox. It seems like there's a symmetry that should make the situation ambiguous. But there isn't. The situation is not symmetric. Bob accelerated. He turned around, he experienced forces that Alice didn't experience. Acceleration breaks the symmetry. Bob's reference frame was not inertial during the acceleration phases. Alice's reference frame stayed inertial the whole time. The laws of physics distinguish between them. Bob is the one who's younger when they reunite, not Alice. This has been tested experimentally, not with humans traveling to distant stars, obviously, but with atomic clocks. In the Hafele-Keating experiment in 1971, atomic clocks were flown around the world on commercial airplanes. When they returned, the clocks had experienced less time than identical clocks that stayed on the ground. The difference matched exactly what relativity predicted. The moving clocks ran slow. Time dilation is real, measurable, and matches Einstein's predictions precisely. We've actually tested this with atomic clocks. In 1971, physicists Joseph Hafele and Richard Keating put atomic clocks on commercial airplanes and flew them around the world, once eastward and once westward. When the planes landed, they compared the clocks that had been flying to clocks that had stayed on the ground. The flying clocks had experienced less time. The difference was tiny. Just a few hundred nanoseconds, but it matched exactly what relativity predicted. Time dilation is real. It's been measured. It's not just a mathematical curiosity or a thought experiment. It actually happens. GPS satellites provide even more dramatic confirmation. GPS satellites orbit Earth at speeds of about 14,000 kilometers per hour or 8,700 miles per hour. At these speeds, relativity predicts that clocks on the satellites run slightly slower than clocks on the ground. The difference is about 7 microseconds per day. That doesn't sound like much, but GPS needs to be accurate to within meters or feet. Light travels about 300 meters or about 1,000 feet in 1 microsecond. If we didn't account for time dilation, GPS would accumulate errors of several kilometers or a few miles per day. The fact that GPS works, that your phone can pinpoint your location to within a few meters or feet, is proof that time dilation is real and that we understand how to calculate it. But special relativity only deals with observers moving at constant velocity. Einstein wanted to extend his theory to include acceleration and gravity. This led to general relativity, published in 1915. General relativity is even stranger than special relativity. It says that gravity isn't a force, not in the traditional sense. Instead, gravity is the curvature of space-time itself. Massive objects like planets and stars warp the fabric of space-time around them. Objects moving through this warped space-time follow curved paths, and we interpret this as the effect of gravity. And here's the crucial part for our discussion. This warping of space-time doesn't just affect space, it affects time too. Time runs slower in stronger gravitational fields. If you're deep in a gravity well, like near the surface of a massive planet or near a black hole, time passes more slowly for you than for someone far away from the gravitational source. This is gravitational time dilation. Let me give you an analogy. Imagine space-time as a rubber sheet stretched tight. If you place a heavy ball on the sheet, it creates a dip. The sheet curves around the ball. Now imagine rolling a marble across the sheet. If the sheet was flat, the marble would roll in a straight line. But with the dip from the heavy ball, the marble's path curves. It might even orbit around the dip. That curved path is what we call gravity. Now imagine that the rubber sheet represents not just space, but time as well. The dip doesn't just curve the path through space. It slows down time. The deeper you go into the dip, the slower time runs. This has been tested too. Clocks at higher altitudes, farther from Earth's surface, and thus in a weaker gravitational field, run faster than clocks at sea level. The difference is tiny, but it's measurable with atomic clocks. GPS satellites have to account for this too. They're about 20,000 kilometers, or 12,400 miles above Earth's surface, where gravity is weaker. General relativity predicts that clocks on the satellites run about 45 microseconds faster per day than clocks on the ground. Combined with the special relativity effect making them run slower, the net result is that satellite clocks run about 38 microseconds faster per day. GPS systems correct for this. Without these corrections accounting for both special and general relativity, GPS would fail within minutes. The most extreme example of gravitational time dilation involves black holes. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. At the center is a singularity, a point where density becomes infinite and the laws of physics as we know them break down. All the mass of the black hole is compressed into this infinitely small point. The mathematics say the density is infinite, though we don't really know what happens at the singularity because our theories break down there. We need a theory of quantum gravity to understand singularities, and we don't have one yet. Surrounding the singularity is the event horizon, the point of no return. Once you cross the event horizon, you can never escape. All paths lead inward to the singularity. Even if you fire your rockets at full power away from the black hole, you'll still fall inward. Space itself is falling into the black hole faster than you can move through space. It's like trying to swim upstream in a river that's flowing faster than you can swim. No matter how hard you try, you're carried downstream. Near the event horizon, space is falling inward, faster than light can travel outward. That's why nothing can escape. Light itself is trapped, pulled inexorably toward the singularity. Near a black hole, time dilation becomes extreme. If you were falling toward a black hole and you looked back at the universe, you'd see time speeding up. Stars would age and die in what seemed like moments to you. Galaxies would collide and merge. Billions of years of cosmic history would unfold before your eyes in what felt like minutes or hours to you. The universe's entire future would flash by as you fell toward the horizon. But if someone far away from the black hole was watching you fall in, they'd see something completely different. They'd see you slow down as you approached the event horizon. From their perspective, you'd take forever to cross it. Your clock would run slower and slower, asymptotically approaching zero. They'd never actually see you cross the horizon. You'd appear frozen in time, forever falling, forever getting closer, but never quite reaching that boundary. The light from you would become increasingly redshifted, stretched to longer and longer wavelengths until it faded away into nothing. You'd fade from view, but from the outside perspective, you'd never actually cross the horizon. From your perspective, though, you'd cross the horizon in finite time. You wouldn't notice anything special happening at the moment you crossed. There's no wall, no barrier, no sign that marks the event horizon. You just keep falling toward the singularity. The horizon is defined by light cones, by the structure of space-time itself, not by any physical object. Once you cross it, your future light cone, the set of all possible futures you could have, points inward. Every possible future leads to the singularity. There's no escape, not because something is pulling you in, but because the structure of space-time itself mandates it. Your future, all possible futures, end at the singularity. This bizarre difference in perspectives is one of the strangest consequences of general relativity. There's no universal now, no absolute present moment that everyone agrees on. Your present depends on your motion and your position in a gravitational field. Time is fundamentally relative and local. Every observer has their own experience of time, their own flow of past to future, and these don't necessarily line up with anyone else's. Einstein's relativity showed that space and time are not separate. They're woven together into a four-dimensional fabric called space-time. An event isn't just located in space or in time. It has 4 coordinates, 3 spatial, and 1 temporal. You need to specify not just where something happened, but when it happened to fully describe an event. Moving through space and moving through time are connected in fundamental ways. When you move faster through space, you move slower through time. When you're deep in a gravity well, bent space-time means time slows down. Space and time are 2 aspects of a single unified entity. This has profound implications for understanding time. Time is not an external absolute thing flowing at the same rate for everyone. It's part of the structure of the universe, inseparable from space, flexible and relative. The rate at which time passes depends on how fast you're moving and where you are in a gravitational field. There's no universal clock ticking away the same for everyone. Each observer has their own time, their own clock, and these clocks run at different rates depending on the observer's circumstances. But if relativity made time strange, quantum mechanics is about to make it even stranger. Quantum mechanics is the physics of the very small, the realm of atoms and subatomic particles. It was developed in the early 20th century, around the same time as relativity. But while relativity deals with very fast things and very massive things, quantum mechanics deals with very tiny things. And at this scale, the universe behaves in ways that seem completely bizarre. In classical physics, objects have definite properties. A ball is in a specific location. It's moving at a specific speed in a specific direction. You can measure these properties and predict where the ball will be in the future. Quantum mechanics says that at the atomic scale, this isn't true. Particles don't have definite positions or velocities, until you measure them. Before measurement, they exist in a superposition, a combination of all possible states. Only when you observe the particle does it choose a definite state. This is famously illustrated by Schrödinger's cat, a thought experiment proposed by physicist Erwin Schrödinger. Imagine a cat in a sealed box with a vial of poison. There's a mechanism that will break the vial based on a quantum event, like the decay of a radioactive atom. Quantum mechanics says the atom is in a superposition of decayed and not decayed until you observe it. Therefore, the cat is in a superposition of alive and dead until you open the box and look. Only when you observe does the cat become definitely alive or definitely dead. Before that, it's somehow both. This seems absurd. Cats are either alive or dead, not both. But at the quantum level, this is how reality works. Particles really do exist in superpositions. We've tested this countless times. The double-slit experiment is a classic demonstration. Fire electrons, one at a time, at a barrier with two slits. Put a detector screen on the other side. Each electron goes through one slit or the other, right? But the pattern that builds up on the screen is an interference pattern, the kind of pattern you get when waves overlap. The electron somehow goes through both slits at once, interfering with itself. It exists in a superposition of going through slit 1 and going through slit 2. Only when it hits the detector screen does it decide where to land. But here's where it gets really strange. If you put a detector at the slits to see which slit each electron goes through, the interference pattern disappears. Now each electron goes through one slit or the other, not both. The act of measuring which path the electron took changes the outcome. It's like the electron knows it's being watched and behaves differently. This is the measurement problem in quantum mechanics. And it's deeply connected to the nature of time. In classical physics, you can observe something without changing it. You look at a ball, you see where it is, and the ball doesn't care that you looked at it. But in quantum mechanics, observation fundamentally changes the system. Before measurement, the particle is in superposition. After measurement, it has a definite state. The measurement causes a collapse of the wave function, the mathematical description of the particle's superposition. And this collapse is instantaneous. It doesn't matter how spread out the wave function was in space. The moment you measure the particle in one location, the probability of finding it elsewhere instantly becomes zero. This has weird implications for time. In classical physics, causality is clear. A causes B, B causes C, always in that order. But in quantum mechanics, things get murky. There's an experiment called Wheeler's delayed choice experiment, proposed by physicist John Wheeler. Here's how it works. You send a photon through a double-slit setup. You can choose, after the photon has already passed through the slits, whether to measure which slit it went through or to let it create an interference pattern. Your choice, in the present, seems to affect what happened in the past. If you choose to measure which slit, the photon went through one slit. If you choose not to measure, the photon went through both slits. But you made this choice after the photon already passed the slits. This doesn't mean you're changing the past. It's more subtle than that. It suggests that the past isn't as fixed as we think. Until you make a measurement, the photon's history is in superposition. It went through both slits and one slit simultaneously. Only when you measure does that history become definite. The past, like the present and future, is in some sense undetermined until observed. Time in quantum mechanics isn't a simple sequence of definite events. It's a web of possibilities that collapse into actuality when observed. Another quantum weirdness relevant to time is entanglement. When two particles are entangled, measuring the state of one particle instantly determines the state of the other, no matter how far apart they are. If you entangle two electrons so that their spins are opposite, and you measure one electron to have spin up, the other instantly has spin down, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance. He thought it showed that quantum mechanics was incomplete, that there must be hidden variables we're not accounting for. But experiments have confirmed that entanglement is real. There are no hidden variables. The correlation between entangled particles really is instantaneous. This doesn't violate relativity because you can't use entanglement to send information faster than light. You can't control what result you get when you measure your particle, so you can't encode a message. But it does suggest that the universe is fundamentally non-local. What happens here can instantly affect what happens far away. And this has implications for how we think about time and causality. Some physicists have proposed that time might not be fundamental at all. It might be emergent, arising from deeper quantum processes. In theories like loop quantum gravity, space-time itself is quantized, broken into tiny, discrete chunks. At the smallest scales, the Planck scale, about 10 to the minus 35 meters, or about 10 to the minus 34 feet, space-time is a foam-like structure. Time as we know it doesn't exist at this scale. It emerges only when you look at larger scales. Just like water seems like a continuous liquid, even though it's made of individual molecules. Other theories suggest that time is an illusion created by quantum entanglement. The flow of time might be a consequence of the way information is distributed and correlated across the universe. In this view, time doesn't fundamentally exist. What exists is a timeless quantum state, and the appearance of time flowing is an emergent property that arises from our perspective as observers within that state. This is highly speculative, and there's no consensus among physicists. But the fact that serious scientists are considering the possibility that time is not fundamental tells you how strange quantum mechanics is. At the deepest levels of reality, time might not be what we think it is. It might not even be real. But if time is relative in relativity and possibly emergent in quantum mechanics, why does it always seem to flow in one direction? Why do we remember the past, but not the future? Why can't we go backward in time? To answer this, we need to talk about the arrow of time and the concept of entropy. You've never seen a broken egg spontaneously reassemble itself. You've never seen smoke flow back into a chimney and turn into burning wood. You've never seen a melted ice cube suddenly freeze back into a cube shape on a warm countertop. You've never seen a shattered glass jump up off the floor and reassemble into a whole glass. These things don't happen. Time has a direction. It flows from past to future, and this flow seems irreversible. This is what physicists call the arrow of time. Now consider what most people don't realize about the fundamental laws of physics. Most of them don't have an arrow of time built into them. Newton's laws work just as well backward as forward. If you film a planet orbiting a star and play the video backward, it still obeys Newton's laws. The orbit looks perfectly natural running in reverse. Einstein's relativity equations work the same forward and backward. If you reverse time in the equations, you get solutions that are just as valid as the forward time solutions. Even most quantum mechanics is time symmetric. If a process is allowed, the reverse process is also allowed at the quantum level. The Schrödinger equation, which describes how quantum states evolve, works the same forward and backward. So where does the arrow of time come from? Why does time only go one way in our everyday experience? Why do we see eggs break but never unbreak? Why do we see ice melt but never see liquid water spontaneously freeze into ice cubes at room temperature? If the fundamental laws don't care about the direction of time, why does the universe care? The answer lies in thermodynamics, specifically the second law of thermodynamics. This law states that in a closed system, entropy always increases over time or stays the same. It never decreases. Entropy is often described as disorder, but that's a bit misleading. A more precise definition is that entropy is a measure of the number of possible microscopic states that correspond to a macroscopic state. Here's what that means with a detailed example. Imagine a room with air molecules flying around. There are about 10 to the 27 molecules in a typical room. That's a 1 followed by 27 zeros. Each molecule has a position and a velocity. At any moment, the room is in a specific microstate, meaning each molecule is in a specific location, moving at a specific speed in a specific direction. There are an enormous number of possible microstates, almost infinite for practical purposes. Now let's think about macrostates. A macrostate is what you can observe without tracking every individual molecule. Things like temperature, pressure, and whether the air is evenly distributed or clumped in one corner. The air is evenly distributed throughout the room. That's a high entropy state because there are many, many different ways the individual molecules could be arranged and still result in air that's evenly distributed. One molecule could be here or a meter over there, another could be near the ceiling or near the floor. As long as on average they're spread throughout the room, you get the same macrostate of evenly distributed air. Now imagine all the air molecules are in one corner of the room. The rest of the room is a vacuum. That's a low entropy state because there are far fewer ways to arrange the molecules to achieve that configuration. They all have to be in that corner. You can't have one molecule way over in the opposite corner because then the air wouldn't all be in one corner anymore. The number of microstates corresponding to all air in one corner is much smaller than the number of microstates corresponding to air evenly distributed. The second law says that systems naturally evolve from low entropy states to high entropy states. They go from ordered configurations with few possibilities to disordered configurations with many possibilities. Why? It's just statistics. It's probability. If you start with all the air in one corner and let the molecules move randomly, they'll naturally spread out. Not because there's a force pushing them apart, but simply because there are more ways for them to be spread out than bunched together. Random motion will explore all possible configurations, and since there are overwhelmingly more configurations with spread out air than with bunched together air, you'll end up with spread out air. An analogy makes this clearer. Imagine you have a deck of 52 cards neatly organized by suit and rank. All spades together, then hearts, then diamonds, then clubs. Each suit ordered from ace to king. That's low entropy. There's only one arrangement that's perfectly sorted this way. Now shuffle the deck once. It becomes disordered. That's higher entropy. Now shuffle again. It's still disordered, probably in a different way, but still disordered. Keep shuffling. The deck stays disordered. Each shuffle puts it in a different disordered state, but you never shuffle it back into perfect order by accident. Why not? Because there's only one perfectly sorted arrangement, but there are over 8 times 10 to the 67 possible arrangements total. That's the number of ways to arrange 52 cards, factorial of 52. Almost all of these arrangements are disordered in the sense that they're not sorted. So random shuffling keeps you in disorder simply because disordered states vastly outnumber ordered states. You're not becoming more disordered in any absolute sense. You're just moving randomly through the space of possible arrangements, and since almost all arrangements are disordered, you stay disordered. This is why a broken egg doesn't reassemble itself. When the egg is intact, all the molecules are arranged in a very specific way. Proteins are folded in specific configurations. Water molecules are in specific locations. The shell is intact with its crystalline structure preserved. There's only a small number of arrangements that constitute an intact egg. That's low entropy. When the egg breaks, the molecules scatter. The shell fractures into pieces. The yolk and white spread out. There are countless ways to arrange scattered egg molecules. That's high entropy. The second law says the system will naturally go from low entropy, intact egg, to high entropy, broken egg. Going the other way, from broken to intact, would require an incredibly unlikely coincidence where all the molecules just happen to move into exactly the right configuration. It's not impossible in principle, but it's so improbable that it never happens in practice. Consider the actual numbers here. The probability of a broken egg spontaneously reassembling is something like 10 to the minus 1 billion. That's a decimal point followed by a billion zeros and then a 1. If you waited the entire age of the universe, 13.8 billion years, and watched a broken egg the entire time, you wouldn't see it reassemble. If you watched 1 trillion broken eggs for 1 trillion ages of the universe, you still wouldn't see one reassemble. The probability is that low. This increase in entropy is what gives time its arrow. When you see entropy increasing, you can tell which direction is the future. The future is the direction where things are more disordered, more random, more spread out. The past is the direction where things were more ordered, more concentrated, more organized. This is why we remember the past, but not the future. Think about what memory is. Memory is a low entropy state. Your brain stores information in ordered patterns of neurons. Certain synapses are strengthened, others are weakened, creating a pattern that represents a memory of an event. Creating this pattern requires decreasing entropy locally in your brain. The neurons have to be in a specific configuration. This is possible because your brain is not a closed system. It gets energy from food and oxygen from breathing. You can decrease entropy locally by increasing entropy elsewhere. You burn fuel, which increases entropy, and use that energy to create ordered structures like memories. But the information in memory is about past events. The ordered state, your memory, was created after the event happened. Your neurons got configured in a certain way after you experienced something. You can't have a memory of something before it happens, because the low entropy state that constitutes the memory can't exist until after the event that created it. This is why causation runs from past to future. Causes must precede effects, because effects are low entropy states created by causes, and low entropy states can only arise after the events that create them. This is also why you can't unbreak an egg or unburn wood or reverse any irreversible process. These are processes where entropy increases. The broken egg has more entropy than the intact egg. The burnt wood and smoke have more entropy than the unburnt wood. Once entropy has increased, it doesn't spontaneously decrease. The system doesn't randomly reorganize itself into a lower entropy state. Time flows in the direction of increasing entropy, always. Now here's the big question. Why was entropy low in the past? The second law says entropy increases over time. So if you go back in time, entropy must have been lower. If you go all the way back to the beginning of the universe, to the Big Bang, entropy must have been at or near its minimum. The early universe must have been in an incredibly low entropy state. Why? We don't know. This is one of the deepest unsolved problems in cosmology. The Big Bang happened about 13.8 billion years ago. In the first moments, the universe was unimaginably hot and dense. All the matter and energy that would eventually form all the galaxies, stars, and planets was compressed into a tiny volume smaller than an atom. The temperature was so high that matter as we know it couldn't exist. Protons and neutrons hadn't formed yet. Even quarks, the building blocks of protons and neutrons, were barely distinguishable as separate particles. Everything was a hot soup of fundamental particles and energy. As the universe expanded, it cooled. Within the first few minutes, protons and neutrons formed. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before this, electrons couldn't stay bound to nuclei because the temperature was too high. Any atom that formed would immediately be blasted apart by high-energy photons. But at 380,000 years, the universe had cooled to about 3,000 degrees Celsius or about 5,400 degrees Fahrenheit. Electrons could finally bind to nuclei and stay bound. Hydrogen atoms formed. Helium atoms formed. These are the first atoms in the universe. Before this moment, there were no atoms. After this moment, the universe was full of neutral atoms. This is also when light could travel freely for the first time. Before atoms formed, the universe was opaque. Photons couldn't travel far without hitting an electron and scattering. But once atoms formed, most of the electrons were bound inside atoms. Photons could travel freely through space. This light, the first light, that could travel freely through the universe, is still around today. We see it as the cosmic microwave background radiation. It's cooled down to about 3 degrees above absolute zero due to the expansion of the universe. But it's the same light that was emitted when atoms first formed. Every direction you look in the sky, you're seeing this ancient light from 380,000 years after the Big Bang. Throughout this entire history, entropy has been increasing. Stars burn hydrogen, increasing entropy. They convert low-entropy concentrated energy, hydrogen nuclei, into high-entropy dispersed energy, helium and radiation. Galaxies collide and merge, increasing entropy. Black holes form and grow, increasing entropy. Actually, black holes are interesting from an entropy perspective. They have enormous entropy. A black hole's entropy is proportional to the area of its event horizon. Larger black holes have more entropy. When matter falls into a black hole, the entropy of the universe increases. Everything that happens increases the total entropy of the universe, or at least keeps it the same. But why did the universe start in such a low entropy state? This is called the past hypothesis, the assumption that the universe began in a very low entropy state. We don't know why this assumption is true. We just observe that it is. If the universe started in a high entropy state, it would have been maximum disorder. It would have been a uniform gas with no structure, no galaxies, no stars, no planets, no life. Everything would be evenly distributed at maximum entropy, and nothing would ever happen because there would be no way to decrease entropy locally. You need low entropy available to drive processes. Life is a low entropy structure maintained by increasing entropy elsewhere. Imagine a cold, empty universe, dark and featureless. That's high entropy. Nothing interesting happens in a high-entropy universe. Everything is at equilibrium. No gradients, no differences in temperature or density, no flow of energy from one place to another. But our universe started with enormous structure at very small scales. Quantum fluctuations in the early universe created tiny differences in density. Some regions were slightly denser than average, others slightly less dense. These tiny differences, imprinted in the fabric of space-time during the inflationary period in the first tiny fraction of a second after the Big Bang, grew over time. Gravity amplified them. Denser regions attracted more matter, becoming even denser. These regions eventually collapsed to form galaxies and stars. This initial structure, these quantum fluctuations, represent low entropy. The universe could have started completely uniform with no fluctuations at all. That would be higher entropy. But it didn't. It started with structure, with order, with low entropy. Why? One possibility is that this is just a brute fact about our universe. It started in a low entropy state, and that's that. There's no deeper explanation. The initial conditions were what they were. Another possibility involves the multiverse. Some theories in cosmology suggest that our universe might be just one of many in a vast multiverse. Most universes in the multiverse might start with high entropy and stay that way forever. Dead and unchanging, featureless voids where nothing happens. But occasionally, purely by chance, a region of the multiverse might fluctuate into a low entropy state. This is incredibly unlikely. But given infinite time and infinite space, unlikely things happen. That low entropy pocket could expand and become a universe like ours, starting with low entropy and evolving toward high entropy. We find ourselves in such a universe not because it's typical, but because only in a low entropy universe can complexity arise. Only in a universe starting with low entropy can you have stars, planets, chemistry, life, observers. This is a form of anthropic reasoning. We observe a low entropy universe because only a low entropy universe can have observers to observe it. All the high entropy universes exist, but nobody's there to notice them because no life can form in a maximum entropy state. This is highly speculative, and there's no direct evidence for it. We have no way to observe other universes if they exist. The multiverse might be fundamentally unobservable, but it's an attempt to explain why entropy was low at the Big Bang, which in turn explains why time has an arrow. The arrow of time, the fact that time flows from past to future and not the other way, is a consequence of entropy increasing. And entropy increases because the universe started in a low entropy state for reasons we don't fully understand. But there's another perspective on time that's even more radical. It's called the block universe, or eternalism. This view takes relativity seriously and suggests that past, present, and future all exist equally. They're all real, all part of the four-dimensional fabric of space-time. Time doesn't flow. All moments in time exist simultaneously, like frames in a film strip. Our perception of time flowing is an illusion, a feature of our consciousness, not a feature of the universe. In the block universe view, your birth, your current moment reading this, and your death all exist at different locations in space-time, but they all exist. They're all equally real. The past hasn't ceased to exist. The future already exists. You just experience them, one at a time, moving along your world line through space-time. It's like watching a movie. All the frames of the movie exist on the film. The whole story is there. But when you watch it, you see one frame at a time in sequence, creating the illusion of motion and flow. This view is consistent with relativity. In relativity, there's no universal present. Different observers have different definitions of now. If there's no universal now, then it doesn't make sense to say the past is gone and the future hasn't happened yet. Instead, all of space-time exists as a single four-dimensional structure. The flow of time is just our subjective experience as we move through this structure. Many physicists find the block universe view compelling because it takes relativity seriously, but it has uncomfortable implications. If the future already exists, is the future determined? Do you have free will? Or is everything you'll ever do already set in stone, existing in the future region of the block? These are philosophical questions as much as scientific ones, and there's no consensus on the answers. But whether time flows or whether it's an illusion, whether the universe is a block or a dynamic, evolving system, one thing we can ask is whether time travel is possible. Can we move through time in ways other than the normal forward progression at 1 second per second? This is where things get really speculative and really fun. Time travel has been a staple of science fiction for over a century. Stories of people visiting the past or the future, changing history, meeting their past selves, creating paradoxes. But is time travel actually possible according to the laws of physics? The answer is complicated. Some forms of time travel are definitely possible. Others might be possible, and some are almost certainly impossible. Let's start with what we know for sure. Time travel to the future is absolutely possible and actually happens all the time. Remember time dilation from special relativity? If you travel at high speed, time slows down for you relative to someone who stays behind. When you return, less time has passed for you than for them. You've traveled into their future. This isn't hypothetical. It's been measured with atomic clocks on airplanes and satellites. Astronauts on the International Space Station are traveling into the future at a very small rate. They orbit Earth at about 28,000 kilometers per hour, or about 17,400 miles per hour. Due to time dilation, they age slightly slower than people on the ground. The effect is tiny, only a few milliseconds over 6 months, but it's real. If you could build a spacecraft that travels at speeds close to the speed of light, you could travel far into the future. Imagine a spacecraft traveling at 99.99% of light speed. Due to time dilation, time on the spacecraft would run about 70 times slower than time on Earth. You could travel for 1 year on the spacecraft, and when you return to Earth, 70 years would have passed. You'd have traveled 70 years into Earth's future, experiencing only 1 year yourself. This is real time travel. To the future, it's allowed by the laws of physics. The only barrier is engineering. We don't currently have the technology to build spacecraft that can reach such speeds, but there's no fundamental law of physics preventing it. Gravitational time dilation also allows time travel to the future. If you could get very close to a black hole, just outside the event horizon, time would slow down dramatically for you. You could orbit there for what feels like a few hours to you, then leave and return to the distant universe. If you orbited close enough to a supermassive black hole, thousands or even millions of years could pass in the outside universe while only hours passed for you. This was depicted in the movie Interstellar, where characters visit a planet near a black hole and experience massive time dilation. That's based on real physics. So time travel to the future is possible, at least in principle. But what about time travel to the past? Can you go backward in time? This is much more problematic. Most physicists think backward time travel is probably impossible. But there are some loopholes in the laws of physics that might allow it under very specific circumstances. One possibility is wormholes. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical tunnel through space-time connecting two distant points. If a wormhole existed, you could enter one end and exit the other end instantly, even if the two ends are light years apart. This would be a shortcut through space. But wormholes could also be used for time travel. Here's how. Imagine you create a wormhole with two mouths, A and B, sitting near each other. Now take mouth B and accelerate it to near light speed, then bring it back. The two mouths are now connected through the wormhole, but they exist at different times. If you enter mouth A, you exit mouth B, but mouth B is in the past relative to mouth A. You've traveled backward in time. This is allowed by general relativity's equations. Wormholes are solutions to Einstein's field equations, but there are problems. First, we don't know if wormholes actually exist. We've never observed one. Second, wormholes, if they exist, are probably incredibly unstable. They'd collapse almost instantly unless held open by exotic matter with negative energy density. We don't know if such matter exists. Some quantum effects can create small regions of negative energy, but whether you could gather enough to hold a wormhole open is unknown. Third, even if you could create and stabilize a wormhole, using it for time travel creates paradoxes. This brings us to the famous paradoxes of time travel. The most well-known is the grandfather paradox. Imagine you travel back in time and kill your grandfather before he has children. If you kill him, your parent is never born, which means you're never born, which means you can't travel back in time to kill him, which means he lives, which means you are born, which means you can travel back and kill him. It's a loop, a contradiction. The grandfather paradox suggests that backward time travel might be logically impossible. There are proposed resolutions. One is the multiverse or many worlds interpretation. When you travel back in time, you don't go to your past. You go to an alternate universe that's very similar to your past. In that universe, you kill your alternate grandfather. That prevents your alternate self from being born in that universe. But it doesn't affect you because you came from a different universe. There's no paradox because you're not erasing your own history. You're just creating a new timeline that branches off from the original. Another resolution is the Novikov self-consistency principle, named after physicist Igor Novikov. This principle states that if time travel is possible, events must be self-consistent. You can't change the past because anything you do when you travel back was already part of the past. If you try to kill your grandfather, you'll fail. Maybe your gun jams, or you miss, or you kill the wrong person, or something else prevents you. The universe conspires to prevent paradoxes. You're free to try, but you can't succeed in creating a contradiction. This is a bit unsatisfying because it seems to take away free will. But it might be the only way to make backward time travel logically consistent. Some physicists take this seriously. If the laws of physics allow time travel, then the universe must have some mechanism to prevent paradoxes, and self-consistency might be that mechanism. Another time travel method is closed time-like curves. These are paths through space-time that loop back on themselves. If you follow such a path, you end up back where you started in space and time. These exist in some solutions to Einstein's equations, like the Gödel metric, a model of a rotating universe proposed by mathematician Kurt Gödel in 1949. In a Gödel universe, you could travel in a loop and return to your starting point in the past. But we don't live in a Gödel universe. Our universe doesn't rotate in the way Gödel's model requires. So this is more of a theoretical curiosity than a practical method. Stephen Hawking, one of the greatest physicists of the 20th century, proposed the chronology protection conjecture. He suggested that the laws of physics might fundamentally prevent backward time travel, even if the equations allow it in principle. His reasoning was that whenever you tried to create a time machine, quantum effects would create infinite energy densities that would destroy the machine before it could function. The universe protects its own chronology, preventing time travel to the past. This is a conjecture, not a proven theorem, but many physicists suspect it's correct. So where does that leave us? Time travel to the future is definitely possible with speed or gravity. Time travel to the past might be possible in very special circumstances involving wormholes or exotic space-time geometries, but it's probably impossible due to paradoxes and chronology protection. We'll likely never build a time machine that lets us visit the past. But even if we can't travel through time, understanding time is crucial to understanding the universe. And this brings us to the ultimate question: what is time really? Is it a fundamental feature of reality, or is it an emergent illusion? This is where we step back and try to put everything together. We've traveled through everyday time: classical physics, relativity, quantum mechanics, entropy, and time travel. We've seen that time is far stranger than it appears. It's not absolute. It's relative, flexible, possibly emergent, maybe not even real in the way we think. So what is time? One perspective, common in physics, is that time is part of the structure of space-time, a dimension like space, interwoven into the fabric of reality. Events have positions in space-time, 4 coordinates specifying where and when. Change is motion through this 4-dimensional space. The flow of time is our subjective experience as we move along our world line, our path through space-time. In this view, time is real, but it doesn't flow. All moments exist. Past, present, and future are human constructs, labels we put on different regions of space-time. But all those regions are equally real. Another perspective is that time is emergent, not fundamental. At the deepest level, the universe is timeless. What exists is a quantum state, a mathematical object that describes all possibilities. Time emerges when we look at the universe from a particular perspective, when we coarse grain, when we group microstates into macrostates and track how those macrostates change. The arrow of time, the flow from past to future, arises from increasing entropy. But entropy is a statistical concept. It's about counting possibilities. It's not fundamental. In this view, time is an illusion created by our limited perspective as observers inside the system. Some physicists go even further and suggest that consciousness creates time. The flow of time, the sense of moving from past to present to future, might be something generated by conscious brains. Our brains create a narrative, a story of our lives, and that story has a temporal structure. We remember the past, experience the present, anticipate the future. But this temporal structure might be a feature of how our brains process information, not a feature of the external world. The universe might be timeless, a static 4-dimensional block, and time is the way our consciousness navigates through that block. This is highly speculative. There's no scientific consensus on whether consciousness plays a role in creating time, but it's worth considering. After all, everything we know about time comes from our experience. We experience time as flowing, but maybe that experience is misleading, a useful fiction our brains create to help us navigate the world. What we can say with confidence is that time is not what common sense suggests. It's not a universal river flowing at the same rate for everyone. It's not absolute, not independent of space, not unaffected by motion or gravity. Time is weirder, more flexible, more mysterious than it appears. And this has profound implications for how we see ourselves and our place in the universe. If the block universe is correct, then your entire life, from birth to death, exists as a four-dimensional structure in space-time. Every moment you've lived and every moment you will live is out there, part of the eternal structure of reality. You're not a thing that exists for a while and then ceases to exist. You're a four-dimensional object, a world line extending through time, and every moment of that world line is real and permanent. This can be comforting. It means that the past isn't gone. It's still out there, still part of reality. The people you've lost, the experiences you've had, they exist in their own time, as real as this present moment. But it also raises questions about free will. If the future already exists, if everything you'll do is already out there in the block, then in what sense do you have free will? Are you just discovering a path that was already laid out? There's no easy answer. Some philosophers argue that free will is compatible with the block universe. Even if the future exists, you still make choices, and those choices determine which path you take through the block. Other philosophers argue that the block universe implies determinism, that everything is fixed and free will is an illusion. This is a debate that goes beyond physics into philosophy and metaphysics. If time is emergent or an illusion, that's even stranger. It means that at the deepest level of reality, time doesn't exist. What exists is something timeless, some quantum state or mathematical structure, and time is just a convenient way we describe patterns in that structure. In this view, saying time is an illusion doesn't mean time isn't useful or isn't part of our experience. It just means it's not fundamental. It's like temperature. Temperature is real. You can measure it. It affects how things behave. But at the fundamental level, temperature is just the average kinetic energy of molecules. It's a statistical property, not a fundamental entity. Time might be similar, a high-level emergent property that's incredibly useful for describing the world, but doesn't exist at the deepest level. Even if time is emergent or illusory in some fundamental sense, it's still the framework within which you live your life. Your experiences are real to you. Your memories, your hopes, your relationships, all of these are structured by time. The fact that time might not be fundamental doesn't make your life less meaningful. It reveals that the universe is stranger and more interesting than you thought. Understanding that time is relative, that it runs at different rates depending on speed and gravity, has real technological applications. GPS wouldn't work without accounting for relativity. Our understanding of time is essential for modern technology. Future technologies, like quantum computers, might rely on understanding quantum mechanics, including its strange relationship with time. If we ever achieve practical fusion energy, it will be because we understand how matter behaves over time at extreme temperatures and pressures. Understanding time also shapes how we think about the future of humanity and the universe. The universe is about 13.8 billion years old. It will continue to exist for trillions of years into the future. Stars will burn out. Galaxies will drift apart as the expansion of the universe accelerates. Eventually, in the far, far future, the universe will reach a state of maximum entropy, the heat death where no more change is possible, where time, in a sense, stops because there's nothing left to change. The universe becomes a cold, dark, uniform state at maximum entropy. No stars, no galaxies, no structure of any kind. Just particles spread uniformly through an ever-expanding space. This is trillions upon trillions of years away, so far in the future it's almost meaningless to think about. But it's the ultimate fate the universe is heading toward according to our current understanding. On shorter timescales, understanding time helps us think about space exploration and the future of our species. If we ever send humans to other stars, time dilation will be a real factor. Astronauts traveling at high speeds will age less than people on Earth. This could make interstellar travel more feasible from the traveler's perspective. A journey that takes hundreds of years from Earth's perspective might only take decades for the travelers if they're going fast enough. But it also means they'll return to a completely different Earth, separated from their original time not just by distance but by centuries. Understanding time also matters for artificial intelligence. As AI systems become more advanced, they might need to model time and change. How do you create an AI that understands causality, that can plan for the future, that can learn from the past? These are questions that require understanding what time is and how it works. If time is emergent or illusory, how does that affect how we should program AI to interact with the world? On a personal level, understanding time can change how you live your life. If you really grasp that time is finite, that your future is limited, it can motivate you to make the most of the time you have. If you understand that your experience of time is subjective, that time flies when you're engaged and drags when you're bored, you can choose to fill your life with engaging activities. If you understand that memories are your only connection to the past, you can appreciate those memories and work to create positive ones. There's also a psychological benefit to understanding time's weirdness. When you're stressed or anxious, you're often worried about the future or ruminating about the past. But the future doesn't exist yet. It's not real in the present moment. The past is gone. It doesn't exist in the present moment. All that exists is now. This is a core insight of mindfulness and meditation practices. By focusing on the present moment, by recognizing that past and future are mental constructs, you can reduce anxiety and stress. Understanding the physics of time supports this. Time is not what you think. The flow from past to future might be an illusion. All you really have is this moment. Some physicists and philosophers find the unreality of time disturbing. Julian Barber, a physicist who's written extensively on time, argues that time doesn't exist at all. That what we call time is just a sequence of static configurations, like frames in a film. Each moment exists on its own. There's no flow connecting them. Our sense of flow comes from memory, from the fact that each moment contains records of other moments. But there's no actual motion through time. This view, called timelessness, is radical. But it's taken seriously by some researchers. Whether time is real or illusory, whether it flows or is a static block, whether it's fundamental or emergent, one thing is clear. Time is one of the deepest mysteries in physics. We've made enormous progress in understanding it. Newton gave us absolute time. Einstein gave us relative time. Time woven into space-time, flexible and dynamic. Quantum mechanics gave us probabilistic time, uncertain and observer-dependent. Thermodynamics gave us the arrow of time, the directionality that comes from entropy. But we still don't have a complete theory of time. we don't fully understand how time works at the quantum level. We don't know if time is fundamental or emergent. We don't know why time has an arrow. We don't know if time travel to the past is possible. These are open questions, active areas of research, and solving them will require new ideas, new theories, maybe even new mathematics. Some physicists are working on quantum gravity, trying to unify quantum mechanics and general relativity into a single theory. This might finally tell us what time is at the deepest level. Others are working on cosmology, trying to understand the Big Bang and why the universe started in a low entropy state. Others are studying black holes, where time behaves in extreme ways, hoping to learn something fundamental about time's nature. You, as someone interested in these questions, are part of this journey. You might not be a professional physicist, but by thinking about these questions, by trying to understand what time is, you're engaging with one of the fundamental mysteries of existence. And that's valuable. Science is not just something done by experts in labs. It's a way of thinking, a way of asking questions and seeking answers. By wondering about time, by being curious, by wanting to understand, you're participating in humanity's quest to comprehend the universe. Let's bring this to a close. We've covered a lot of ground tonight. We started with everyday time, the time you experience, the time measured by clocks, the psychological time that speeds up and slows down depending on what you're doing. We looked at how ancient people measured time with sundials and water clocks, how mechanical clocks revolutionized society, how atomic clocks measure time with incredible precision. We saw that even at this everyday level, time is somewhat subjective, created by your brain based on your experiences. Then we moved to classical physics and Newton's absolute time, a universal clock ticking the same rate everywhere in the universe. This worked well for 200 years, explaining motion and gravity with great accuracy. But cracks appeared, like the strange behavior of light, always traveling at the same speed regardless of the observer's motion. Einstein shattered absolute time with special relativity. Time is not universal, it's relative. It depends on your motion. Travel fast and time slows down for you. This is time dilation, confirmed by countless experiments. Then general relativity added gravity to the mix. Gravity warps space-time. Time runs slower in stronger gravitational fields. Near a black hole, time can slow to a crawl. Space and time are not separate. They're woven into a four-dimensional fabric called space-time. Quantum mechanics made things even stranger. At the quantum level, particles don't have definite properties until measured. They exist in superpositions, combinations of all possibilities. Measurement causes a collapse, and this collapse seems instantaneous, raising questions about causality and time. Experiments like Wheeler's delayed choice suggest that the past isn't fixed until observed. Entanglement creates correlations across space that seem to defy our usual understanding of cause and effect. The arrow of time, the fact that time only goes forward, comes from entropy. The second law of thermodynamics says entropy increases in closed systems. This gives time a direction. The future is the direction of increasing disorder. The past is the direction of decreasing disorder. But we don't know why the universe started in a low entropy state, why entropy was low at the Big Bang. This is one of the deepest mysteries in cosmology. Time travel to the future is possible through speed or gravity. Time travel to the past might be possible through wormholes or closed time-like curves. but it creates paradoxes and is probably prevented by the laws of physics through mechanisms like chronology protection. Finally, we asked what time really is. Is it a fundamental dimension, part of the structure of space-time, as relativity suggests? Is it emergent, arising from deeper quantum processes, not fundamental at all? Is it an illusion, a construct created by conscious minds to make sense of change? We don't have a final answer. This is still an open question, one of the biggest unsolved problems in physics. But we can say this: time defies common sense. It's not a simple, universal, absolute thing. It's complex, relative, possibly emergent, deeply mysterious. Understanding this changes your perspective. It humbles you, because it shows how limited our everyday intuitions are. The universe operates in ways that contradict our direct experience. But it also empowers you because it shows that humans, despite being small and limited, can understand these counterintuitive truths. We can uncover the hidden nature of reality through careful thought and experiment. The next time you look at a clock, remember what you've learned tonight. That clock is measuring something far more complex than you imagined. Something that's not absolute, not universal, not even necessarily fundamental. Time might be a useful construct that helps you navigate the world but doesn't exist at the deepest level. Or time might be real but woven into space-time in ways that make it flexible and relative. Either way, it's far more profound than the simple ticking of seconds. In fact, it's beautiful. The universe is far more interesting than a simple clockwork mechanism. It's a place where time can stretch and compress, where past and future might exist simultaneously, where the flow of time might emerge from increasing entropy and the structure of our consciousness. This is the universe we live in. Strange, mysterious, beautiful. You are part of this universe, made of atoms forged in stars, living in a time created by the Big Bang, experiencing a flow of duration that might emerge from entropy itself. Even if time's fundamental nature remains mysterious, it's your experience. Your memories, your anticipation of the future, these are real to you. They're the fabric of your life. Understanding that time is strange doesn't diminish your experiences. It enriches them. It shows you that you're living in a universe that's far more wonderful and mysterious than you imagined. So embrace the mystery. Be curious. Ask questions. Think about time. Think about existence. Think about your place in this strange, beautiful universe, whether it's timeless or filled with flowing moments. Because even if time's nature remains uncertain, your ability to think about it, to wonder, to understand, that's real. That's what makes you human. That's what makes life meaningful. Thank you for joining me on this journey through time and beyond time. If you found this exploration valuable, if it changed how you see the world, a like or subscribe would mean a lot. It helps me keep making these deep dives into the cosmos and the fundamental questions of existence. And remember, whether time flows or stands still, whether it's fundamental or emergent, the wonder you feel when contemplating these questions is as real as anything in the universe. Good night, and may you never look at time the same way again.